Let's continue with ZEUS training, Section 10, Spline. So we have the following spline methods in ZEUS to generate the spline matrix, which is called GKG. We have the infinite plate spline, which is specified by the Spline1 bulk data card. The thin plate spline, specified by the Spline3 bulk data card. The beam spline, which is the Spline2 bulk data card. We have rigid body attachment, specified by the attach bulk data card, and then finally the zero displacement spline, which is the Spline0 bulk data card. And the purpose of the spline module is to map the FEM model displacements to the aerodynamic model as shown in the figure. So if our rigid body model, our rigid structure is shown in the red here, and then our aerodynamic model is shown in the red here, we can see that this deformation in the structure model should lead to this deformation in the aerodynamic model. So we use the different spline methods available to us to accomplish this mapping. So the spline matrix transfers the displacement computed at the structural G set degrees of freedom to the aerodynamic K set degrees of freedom by this HK is equal to GKG times X. Now, based on the principle of virtual work, the transposed spline matrix, GKG, can transfer the forces computed at the aerodynamic K-set degrees of freedom to the structural G-set degrees of freedom. So we have the forces on the structure grids equals the transpose of GKG times the forces on the aerodynamic grids. And a general guideline used in the spline is all aerodynamic grids should be within the domain of the structural grids to avoid extrapolation. And these are the bulk data cards we use to define the spline. So we have our Spline1, Spline2, and Spline3 cards up here. They all refer to both a set G and set K. So the set G field refers to the set 1 or set 2 or set add bulk data cards, which list out the structural grid points. The set K refers to the PanLST1, PanLST2, and or PanLST3 cards to list the aerodynamic boxes. Meanwhile, the attach card, which is the rigid body attachment, directly lists the grid point in the bulk data card, so it only has a set K field to refer to the PanLST cards. And then the Spline0, the zero displacement, of course, that does not refer to a structural grid point. That refers to the PanLST cards via the set K field. Meanwhile, we have the plot mode card, which plots the interpolated mode shapes on the aerodynamic model. Then we have the SPLINEM card, which can save or retrieve the spline matrix. So after you have your model set up, you can save the spline matrix and then retrieve it on restart jobs to avoid ZEUS recomputing the spline matrix. Then we have the SPLINEF card to modify the force spline matrix. On the last slide, we said that the force spline matrix is just the transpose of the displacement spline matrix. That's true in the default case. However, you can override the force spline matrix, and we'll see some reasons why you might want to do that later on. And then we have the d.o.f, which adds additional degrees of freedom on the structure model to allow you to create a better spline matrix. This is usually used in conjunction with the beam spline, where you can add rotational degrees of freedom that do not exist in the structure model to be made available to the beam spline or the rigid body attachment. So first, let's talk about the infinite plate spline, which is the Spline1. The infinite plate spline method is derived from an analytical solution of an infinite plate that first fits the deformation at a set of structural grid points projected on a plane into a deformed infinite plate. So if we have our structure grids here, first we take all of our grids, the original grid locations, and project those onto a plane, which is our spline plane. Then we see what the deformation is of each of those grids, and that deformation will define our deformed infinite plate. Now we take the deformed infinite plate, and the deformation at any point on the aerodynamic grids on the plate can be calculated from the deformed infinite plate solution. So we just take this analytical solution of our deformed infinite plate, find out the xy coordinates of each of the aerodynamic grids, and then we calculate what the displacement is. So the IPS method requires at least 3 non-collinear structure grid points to define the plane, which is called the spline plane, and all of the aerodynamic grids should be within the domain of the structure grids to avoid extrapolation. So you can see that our analytical solution here, we have an infinite plane. So in theory, the aerodynamic boxes could be anywhere on this infinite plane. However, you can see that if we go outside the domain of the structure grids, what we're doing is extrapolating the deformation of our structure grids to these points outside the region of the structure grids. And we want to avoid extrapolation because we all know that in general, extrapolation is bad. So the goal is, in our structure model, we want the structure grids to extend and cover the entire domain of where the aerodynamic boxes would be. Next, the IPS method is the best spline method when splining between plate-like structure components and wing-like aerodynamic components, which are the C07s. And then finally, if 2 structure grid points share the same location on the projected spline plane, then the spline matrix becomes singular. And so we have some checks in ZEUS to make sure this condition is not violated. So this is the bulk data card. We have an identification number, which doesn't matter except for error output. So you want to avoid reusing the same ID number just to help with the error output so you don't get confused. The model field is not used. The CP field refers to a Chord 2R card to define the spline plane. Now usually by default you leave the CP field blank, so if no CP is specified, then the plane defined by the macro element specified in the PLTMODE card is used for the spline plane. So usually with a wing, you just want to use the plane of the C07 as the spline plane, so CP can be left blank. However, if you're using the spline plane on a body, or if you would like to override what that spline plane is, you can do that with the CP field here to refer to a Chord 2R. Next, we have the set K field. So this refers to the PLTMODE, PLTMODE, and or PLTMODE bulk data cards that list the aerodynamic box identification numbers. Now for when splining a wing or a C07 elements, usually you want to have one spline card for each C07 because in general each C07 could define a different plane, which is the spline plane. So if you have a wing made up of multiple C07s, your dihedral angle may be slightly different between each of the C07s. So ideally, each C07 would have its own spline card so that the boxes on that C07, the spline plane defined for those boxes, is the spline is the plane that the C07 lies on. If you have multiple C07s referenced by a single spline card, then the spline card must choose one of those C07s to use as the spline plane, and then all of the other boxes on the other C07s will use that original spline plane. So a warning message will be printed out in ZEUS if you have multiple C07s referenced by a single spline card. In practice, that doesn't cause problems. It's just something to be aware of. So it's best, or it's recommended to have one spline card or multiple spline cards for each individual C07. Where it's actually needed is if you have a winglet and a wing. If you try to spline the wing and the winglet with the same spline 1 card, then the spline plane would end up probably being the wing, which would not be valid for the winglet because the dihedral angle between the wing and the winglet is much different. So in that case, you definitely would want to spline the winglet and the wing using different spline cards so that they can each use the proper spline plane. Next, we have the set G field. This refers to the set 1, set 2, or set add bulk data cards to list the structural grid points to which the spline is attached. And then we have the DZ and the EPS on the next slide. So the DZ is the linear attachment flexibility. The default is 0, but it's a real number greater than or equal to 0. So the attachment flexibility in units of area is used for smoothing the interpolation. And if dz equals 0, which is the default, the spline will pass through all of the deflected grid points. And if dz is much greater than the spline area, then a least square plane fit will be applied. So most often, you can just leave that at 0. But if you know what you're doing and you want to change that, feel free. Next is the EPS, or epsilon. This is a multiplication factor to obtain a small tolerance to detect any duplicated location of the structural grid points. So if we go to remark 3 here, if any 2 or more structural point locations projected onto the spline plane are nearly the same, then the spline matrix becomes singular. So epsilon is used to detect this condition. And the way we calculate the tolerance, it's epsilon times ref C, where ref C, of course, is the reference chord defined by the arrow Z bulk data card. And here's an illustration of the Spline 1 card in action. So we have our structure grid points are the red points, then we have the aerodynamic model. So you can see that the domain of the structure grid points overlaps with the aerodynamic model, and we don't have any extrapolation going on. So then when we use these grid points, then this will be our interpolated mode shape on the aerodynamic model. The deformed structure grid points is not shown here. This is just the original structure model and the original aerodynamic model. And then here we're showing only the deformed aerodynamic model. And we're using the plot mode card to visualize this displacement. Next we have the thin plate spline, which is spline 3, also called the 3D spline. So the thin plate spline method generalizes the infinite plate spline method by incorporating some 3D aspects into the analytical solution of the IPS method. And the thin plate spline method maps the deformation at a set of scattered structure grids in the 3D domain to a set of aerodynamic grids. And the thin plate spline method is the best spline method when splining a set of structure grids located on the fuselage surface and the corresponding aerodynamic body component, or the body 7. So shown here's an example. We have several structure grids distributed out among the fuselage, and then we have our aerodynamic grids, our aerodynamic boxes also describing the fuselage here. So you can see they overlap very well, and this is kind of a 3D shape. And so we select several structure grids scattered throughout this structure and then use the spline 3 to map this deformation. So the thin plate spline method requires at least 4 non-coplanar structure grids. That is, if all of the structure grid points are coplanar, then the spline matrix would become singular. And similar to the infinite plate spline, if 2 structure grids are coincident, then the spline matrix also becomes singular. And this is the spline 3 bulk data card. So we have the ID number. Model and CP are not used. Then we have the set K and set G, which are the same definitions as spline 1. DZ is not used. And then finally we have the epsilon, which also functions the same as the spline 1. So here, once again, we use the epsilon times the reference C, and if the grids are within are closer together than that, then ZEUS will print a warning message. And finally, all of the structural points cannot be located in the same plane, or else the method breaks down. So the EPS will also detect that. Next, we have the beam spline, which is spline 2. Quite often in older structure models, we don't see it so much today anymore, but the wing and the body FEA models are approximated by a structural beam element model. So the beam spline method is created to handle this kind of spline problem. All of the structure grids in this method are first projected onto a line called the spline line, along which the infinite beam is located. So for our wing, we have our structure grids located approximately along the spline line. So then we take our spline line and project all of the structure grids exactly onto the spline line, and then calculate the deformation of each of those grids to find the deformation of this infinite beam. Same thing with the fuselage here. We project the grids onto the spline line, and then map the deformations of those grids to get the equation of this infinite beam deformation, and then map that back to the aerodynamic model. So we have an analytical solution of a deformed infinite beam is derived to satisfy the given deformation at these structural grids. Then we connect the aerodynamic grids to the deformed beam with rigid bars, and the deformation at the aerodynamic grids is then obtained. And this is done internally in ZEUS. Now, because both the translational and the rotational degrees of freedom at the structure grids are required by the analytical solution, any constraint imposed on those degrees of freedom will lead to incorrect spline results. And if, once again, if two structure grids are coincident on the projected line, then the spline matrix will be singular. So the difference with the beam spline method as opposed to the spline 1 and the spline 3 is that the rotational degrees of freedom of the structure grids are used. We didn't mention this earlier on the spline 1 and spline 3, but for spline 1 and spline 3, only the translational degrees of freedom of the grids is used. The rotational degrees of freedom are not considered. But in the beam spline, both the translational degrees of freedom and the rotational degrees of freedom are used. So you want to make sure not to constrain the rotational degrees of freedom of these grids in the structure model if you're using the beam spline method. So this is the spline 2 bulk data card. The second note here on the spline 2, which differentiates itself from the spline 1 and spline 3, the spline 2 beam spline does not ensure the conservation of forces. Therefore, spline 2 is not recommended for loads recovery at those structural grids using the plot trim or the plot time bulk data cards. Of course, if your structure model, if the only option you have is beam spline, then you're going to use it. Just be aware that if you try to recover forces, they won't be accurate with the beam spline method. So a way to work around this, if we go back to our diagram here, if you can modify the structure model and add rigid bar elements out here, and you create your own structure grids out at the boundary of the wing here, and then connect those structure grids to these structure grids using R-bar elements, and then the same thing with the fuselage. You scatter out grid points and then connect them using R-bars. Then you can use the spline 1 with the wing, and you can use the spline 3 with the fuselage. And then when ZEUS maps the forces of the aerodynamic boxes back to the structure grids, the conservation of forces will be guaranteed. So the set K, set G, DZ, and EPS are the same as the spline 1. Then we have the CID field. This is a rectangular coordinate system whose y-axis defines the spline axis, that is the line of the beam. And this field is ignored for body 7 elements. That's because for body 7 elements, the coordinate system that's used to define the body, the x-axis of that is used as the spline axis. And then this coordinate system is defined in the Nastran basic coordinate system. That's what this point 2 is saying. So this chord 2R card, you'll define it in the Nastran basic coordinate system, and then ZEUS will apply the transformations to convert it to the aerodynamic coordinate system for you. And then lastly, we have this curve entry. This is the curvature effects of the torsion stiffness, where the default is 1. Now, MSC Nastran does not include the curvature effects, and so if you want to match your results from MSC Nastran analysis, then you'll need to specify curve equals 0. And then that will match what Nastran is doing in its beam spline method. Next, we have the rigid body attachment. So the rigid body attachment connects a set of aerodynamic grids to a single structural grid point by rigid bars. All of the displacements at these aerodynamic grids follow the 6 degrees of freedom motion of the single structure grid based on rigid body motion. So all 6 degrees of freedom of this grid point are used. So both the translational and the rotational degrees of freedom to map the aerodynamic boxes to this single grid point. So an example here, we have an underwing store, which in the structure model is modeled as a point mass, while in the aerodynamic model, the surface is modeled like so. So in this case, the rigid body attachment method, which is the attach bulk data card, will translate the motion at the structure degrees of freedom to the aerodynamic panel model. And then we could see this attach method being used for the pylon if we have very few grids defining the pylon in the structure model. So this is the bulk data card. So we have the ID number, which once again is only used for error messages. The model field is basically ignored. You can put whatever you want there. Then the set K refers to the PAN-LST cards to define the aerodynamic boxes. And then ref grid is just the ID number of the structure grid point. So this does not refer to set 1 card. Next, we have the SPLINEF card for the force mapping. So this card generates the force spline matrix to map the aerodynamic forces at the aerodynamic grids to the structure grids by altering the Spline 1, Spline 2, or Spline 3 bulk data cards. So by default, the force spline matrix is computed as just the transpose of the displacement spline matrix. But using the SPLINEF card will modify this force spline matrix. So once again, if there are no SPLINEF cards, then this UGFRC just equals UGTKG. But using this card will modify this matrix. So if we go to the next card here, we'll explain what happens. So the ID spline field refers to a Spline 1, Spline 2, or Spline 3 card. And then in this Spline 1, Spline 2, or Spline 3, for the force spline matrix, we're going to change the set of structure grid IDs. So the set G that exists in the Spline 1 or Spline 2 or Spline 3, which defines the displacement spline, is going to be replaced by the set 1 of the SPLINEF card for the force spline matrix. So the set 1 refers to the set 1 or set add cards to list a set of identification numbers of structure grid points that are used to generate the force spline matrix. Why do we want to do that? That's remark 2 here. To ensure continuous displacement and slopes at the aerodynamic grid points by the displacement spline matrix, the generation of UG-TKG may need more structural grid points. However, to achieve a good force spline, it's recommended to select less structural grid points involved in the UG-FRC matrix. This is because one aerodynamic box produces only one aerodynamic force. So if there are more than one structural grid points located on one aerodynamic box, then the force spline matrix needs to split that aerodynamic force and distribute it among more structural grid points. This may result in an irregular distribution of the force distribution at the structural grid points. Now note that based on the principle of virtual work, the conservation of total force is ensured, but it may result in a poor distribution of forces if the structural grid points involved in the force spline matrix are not carefully selected. And this poor distribution of forces can lead to phantom internal moment forces being applied to the structure. And we'll see that a few slides later here. Meanwhile, let's go to the plot mode card, which displays the mode shapes. And we recommend always including several plot mode cards so that you can visualize the interpolated mode shapes on the aerodynamic model. Usually, if you've set up your spline incorrectly, you'll see that right away when you plot the mode shapes. The plotted mode shapes will look terrible if your spline is set up incorrectly. On the other hand, usually if the mode shapes look reasonable using the plot mode card, then that will indicate that your spline is correct. So we have a set ID, which is an identification number. Then we have the sim entry to set the symmetry condition. So remember in ZEUS, we can have either a half span or full span model. And then for the half span model, we import both or either the symmetric or the anti-symmetric mode shapes. So for a half-span model, the sim should be either sim for the symmetric modes or anti for the anti-symmetric modes. And for a full-span model, sim should be asim for the asymmetric condition. So this symmetry condition will match the symmetry condition specified in the assign FEM card. Next we have mode, which is the index of the structural modes. So the plot mode generates a data file which contains just one interpolated structural mode with the index equals mode. Next we have max displacement. This is a fraction of the reference chord defined by ref C to define the maximum displacement of the mode. So the maximum displacement that is plotted is calculated as max DISP times the reference chord. So the default is 1. So by default, the maximum displacement of any aerodynamic grid in this plotted mode shape is just equal to ref C. Next we have the form, which must be equal to tecplot. ZEUS only supports tecplot for the mode shapes. And then we have file name, which is just the name of the file. And these are some examples of some interpolated mode shapes on the aerodynamic model. So we have a transport aircraft, and then we have a fighter aircraft over here. So just visually looking at these, if we look over here, we can see that the motion of the engine and pylon follows the wing, and it's connected to the wing. So that indicates that we have a correct spline among all these components. Likewise here, this underwing store is following the motion of the wing. So this indicates that we have a proper spline setup. And of course, you also can compare visually this mode shape to your structure mode shapes. So when you compare those two, then they should look similar. So these are some modeling guidelines for the spline. First, you want to perform the spline on a component by component basis. So if we go back to the previous slide here, for example, this wing, you'll set the spline up for the wing, then you'll go on and set the spline up for this pylon, then you'll set the spline up for this engine nacelle, and so on. So you'll go component by component. Next, the selection of the spline method depends on the type of components in the ZEUS aerodynamic model and the type of elements in the FEA model, as we see in this table. And just a note, most of the errors in our experience that we've seen in the aeroelastic analysis can be attributed to an incorrect spline input. So setting up the correct spline is very important. So if we go look at this table to determine what spline method to use, if we have a C-Aero 7 in ZEUS and our FEA element is a plate type of element, then we would want to use the spline 1 method. If our FEA element is a beam type of element, and then our ZEUS is either a body 7 or C-Aero 7, we'd want to use spline 2. If we have 3D distributed spatial grids for either body 7 or C-Aero 7, we'd want to use a spline 3. Now, a note here, if you have a detailed wing box model, you may say, oh, those are 3D distributed grid points, and then I have a C-Aero 7 to define my wing, therefore I want to use spline 3. Usually no. Even if you have a detailed wing box in your structure model, that is still kind of a plate type of element. What you want to do is select grid points from that wing box and then use the spline 1 method for the wing. You want to be careful not to choose grids that, when projected onto the spline plane, become the same location. So the easiest way to do that is choose grids only on the upper surface or choose grids only on the lower surface. And then furthermore, you want to make sure to choose grids that will not represent local deformation. So you want to choose grids usually that are on the ribs and spars, or the intersections of those ribs and spars. That way you can guarantee that the motion of those grids represents the overall motion of the wing. If you choose some wing skin grid point that's just sitting out in the middle in between your ribs and spars, that grid may have local deformation, which is just the deformation of the wing skin. You would not want to choose that for your spline point because that motion does not represent the overall motion of the wing. It's just local deformation. Next, we have just a single grid point in the finite element model. So that can be mapped to either body 7 or C07 using the attach bulk data card. And then, as I was just saying, if we have a detailed structure model with grid points on both the upper and the lower surface, if you were to choose all of these grid points, then the first task that ZEUS will do is map those grid points onto the spline plane. So you can see when we do that, this upper grid and lower grid get mapped to the same point. And so this will lead to a singular spline matrix. So you want to select grids only from the upper surface or only from the lower surface, but not both. Or you can choose internal grids that are hard points that represent the ribs and spars. Next, let's talk about spline for discontinuous structure. For example, a control surface such as an aileron. So this example here, we have a control surface where a discontinuity occurs between the side edges of the main wing and the control surface, as well as discontinuous slopes that occur along the hinge line. So it's important to accurately transfer these discontinuous displacements and slopes from the finite element analysis grid points to the aerodynamic model. So in our structure model, if we have these grid points, note back here we've got two grids. Grid 6 is associated with the wing. Grid 7 is associated with the aileron here. And then in our aerodynamic model, we have these boxes. So in this example, we would want to choose the aerodynamic boxes 1 through 6, and then 7, 8, 10, 11 as our wing spline. And then we want to choose these structure grids 1, 2, 3, 4, 5, 6, and 8 and 9. Meanwhile, for the aileron, we would just choose, and that would be the spline 1. And then for the aileron, we'd choose aerodynamic boxes 9 and 12, and then we'd choose the structure grids 5, 7, 9, and 10, and use spline 1 as well for that to map those. Now, usually, of course, you'd have two grids here at 5 and two grids at 9. So one grid would be with the wing, one grid would be with the aileron. Just for illustration purposes, we have the same grid here. So, like I said, separately apply spline 1 for the wing and for the aileron. If you try to set up one spline and choose all of these boxes and all of these grids, then of course you're going to get some weird, ZEUS is going to try to smooth over the deformation between the wing and the aileron back here, which is obviously incorrect. So the rule of thumb here is if you ever have a discontinuous structure, then that should be a separate spline when you're setting up the spline in ZEUS. On the other hand, when you have a continuous structure, you want to have one spline, and I believe we'll see that on the next slide. Okay, so next, ensuring a continuous structure across two adjacent C07 macroelements. So now if we have a non-trapezoidal wing as shown here, this requires two C07s to model that. However, we want to ensure a continuous aerodynamic model displacement over the continuous structure. This requires an appropriate selection of FEA grids. So we're going to have two separate spline cards. So the first spline card will be for this C07, and the second spline card will be for this C07. However, for both spline cards, because this is a continuous structure, we want to refer to all of these structure grids. So for this C07, for this spline card, we'll refer to all of the structure grids 1 through 12. And then for this C07, we'll refer to all of the structure grids 1 through 12. The reason for that is when we create this infinite plane, the infinite deformed plane for this C07, if we use all 12 of these grids, and then for this C07, when we create this infinite plane, if we refer to all of these grids, you'll see that if these two C07s lie in the same plane, then that deformed plane defining the deformation of these 12 grid points would be exactly the same. That ensures that we have a continuous deformation between these two C07s. So we'll get a smooth splined mode shape. If we were to select only grids 1 through 8 for this C07 and only grids 5 through 12 for this C07, then those infinite deformed spline planes would be different. And so we wouldn't get a continuous deformation at the boundary of these two C07s, which is incorrect. So once again, if you have a continuous structure model, it's okay to have multiple spline cards. However, for each individual spline card, you want to refer to all of the structure grids that are part of that continuous structure. Next, we want to have accurate rotational structural degrees of freedom for the beam spline method. And as we've said, unlike the IPS and TPS methods that only use the translational displacements at the grid points, the beam spline method requires both translational and rotational displacements. However, often in the structural finite element analysis, the translational displacements are included as the analysis set degrees of freedom, and the rotational degrees of freedom are left out of the A set. And the exclusion of these rotational displacements for the A set degrees of freedom in the beam spline method will of course lead to incorrect spline results on the aerodynamic model because we need those rotational degrees of freedom. Also, in the case of using GVT measured modes that normally involves only the translational degrees of freedom, applying the beam spline method may lead to inaccurate spline results. And usually measuring the rotational degrees of freedom by GVT is very costly. Therefore, the solution is to use the SPLN d.o.f, or spline degree of freedom, bulk data card to create the rotational degrees of freedom from the translational degrees of freedom. So we'll see how to do that next. No, we won't. So in the spline d.o.f card, you'll pick two grid points, and ZEUS will measure the translational degrees of freedom from those two grid points, and then you can calculate what the rotational degree of freedom of those grid points would have been had they been included. So ZEUS allows you to create these rotational degrees of freedom based solely on the translational degrees of freedom. Then you can make use of those rotational degrees of freedom in your beam spline method or your attach method. Then next we'll talk once again about the extrapolation here. So the structure finite element analysis models can end up smaller than the aerodynamic model, such as when modeling a wing torque box to represent the whole wing, as shown here. So the aerodynamic model is shown in green, the structure model is shown in blue. And the structure guys see no reason to extend the model out to the boundary of the wing because that's not important. What's important is the wing box. So this finite element analysis wing that does not fully extend to the leading and trailing edges of the wing may result in an inaccurate spline due to extrapolation. Another example is the beam type element model of a fuselage. Since the nose section of the fuselage is often considered a non-structural part, the beam model may end up shorter than the actual fuselage length. And so we want to avoid extrapolation. So one way to do that is to go back to your structure model and add additional grid points. So we add these red grid points as shown here. Then we connect them to the structure model using rigid bar elements, for example, R bars. Then we can use these structure grid points in our spline so that we avoid the extrapolation. Now when we add these grid points and the R bars, of course that's not going to affect your natural, your generalized frequency. It won't affect your mode shapes. However, we're just adding these points to make available to us for the spline. Oh, okay, so here is the force spline. So the transposed spline matrix can transfer the forces at the aerodynamic grid points to the structure grid points. And based on the principle of virtual work, the conservation of total force is guaranteed. However, it does not guarantee the conservation of moment. So, to ensure an accurate force spline, it's recommended that the structural grid points selected for the spline be coarser than that of the aerodynamic grid points. And if we have more than one structural grid point located within one aerodynamic box, then we have this following problem. So we have two structure grid points lying within this one aerodynamic box. So this one box generates this force. And now the force spline matrix needs to map this force to those two structure grids. So one possible way it might do that is say, okay, I'm going to take this force and map it to my force 1 and force 2. Now, of course, force 1 plus force 2 equals Fa, but you can see that we've introduced a moment, a phantom moment force, which is not accurate. So, when we set up the force spline matrix, it's recommended to choose fewer structure grids so that this problem does not occur. Furthermore, selection of the structural grids at the structural hard points is recommended so that the aerodynamic forces are applied at the hard points in the structure. If you have grid points just laying out on the wing skin somewhere and then you try to apply these huge aerodynamic forces and then you do a detailed stress analysis in Nastran, of course you're going to get huge local deformations on the wing skin, which is not accurate. However, if you apply the aerodynamic forces at the hard points, the intersection of ribs and spars, then the structure is able to withstand those forces. So the SPLINEF card allows the user to select the structure grid points to be different between the force spline and displacement spline.